Hello everyone, welcome. My name is Miguel, and today I'm going to tell you about our paper on the generalization of learning-based 3D reconstruction. This is joint work with my colleagues Walter, Sanfei, Nitish, and Josh. Let's dive right into it. Occupancy networks, or OCNET, was a paper introduced at CVPR 2019. The key idea is to represent shapes as a level set of a continuous scalar field that models occupancy. Point is labeled as occupied if it lies inside the object mesh, and unoccupied otherwise. We noticed that if OCNET was tested on objects that were not seen during training, performance significantly degrades. In this example, given 5 observations of a foldable phone, note how both OCNET and our model perform similarly when training data includes the cell phone category. However, if we exclude cell phone data from the training set, OCNET's performance degrades quite significantly, while our model still performs reasonably well. Tatarchenko and colleagues showed that most approaches for theory reconstruction are performing categorization, and hypothesized that the main problems were the coordinate system, the metrics, and the dataset. We argued that those factors are not sufficient to explain this behavior, and proposed representation and multi-view aggregation biases in our model to deal with out-of-distribution 3D reconstruction problem. As a summary, our points are that we need to represent 3D points in the view-centric coordinate system, but in addition, we want to represent input observations with spatial feature maps, and we want to aggregate multiple views via variance cost. This is a depiction of our model. We dub it 3D for 3D. It begins by encoding each input observation with a fully convolutional encoder-decoder with tight weights. The output of this encoder-decoder is a spatial feature map that preserves the spatial resolution of the input. To predict occupancy for a 3D point, Pj, we project it into the feature maps and sample them at discrete locations. These features that are sampled are then concatenated with the point XYZ coordinates in the camera coordinate system and the camera position itself, and then fed through an MOP-G that outputs a feature GI for each point and each view. We aggregate information across views by taking the mean and variance in a similar fashion to cost-volume approaches for multi-view stereo. Finally, an MOP takes this mean and variance and predicts an occupancy value. Here we show some results, a comparison between occupancy network and our model. In this particular experiment, we want to see the performance when both models are trained and tested on the same object categories. We take the 13 most frequent ShapeNet categories and train and test both models in that case. We can see how in this experimental setup, OCNET and 3D4-3D perform similarly, while 3D4-3D has a slighter edge on high-frequency geometry. On our second experiment, we take both OCNET and 3D4-3D and train them on just the airplane, chair, and car categories, and test them on the rest of the categories in ShapeNet. We can see here how OCNET tends to snap to the prior learned from training data. We hypothesize that this is due to representing a 3D object via 1D leading code that is more prone to make the model work on a categorization regime. However, we see that with 3D4-3D, given its inductive biases in the model architecture, we can perform much better reconstruction of out-of-distribution categories. Finally, these are our conclusions. Learning-based 3D reconstruction is a promising direction to allow algorithms to reason about semantics. Recent approaches like OCNET inadvertently perform categorization instead of reconstruction, generalizing poorly to object categories seen during training. Finally, we show that our model employs several architectural biases that enable 3D reconstruction of out-of-distribution object categories, obtaining very successful results. Please go read our paper to see more results, and I hope you like the presentation. Bye-bye.